So the next lecture will be given by Professor Spyros Chatzivasileiadis from DTU. He's a professor at DTU Wind over there. So I'm leaving you to guess what's the main source of power in Denmark. They have a dedicated department for it. Huh? So we'll be talking about machine learning for power system, asking ourselves the question, is it time to trust it? So Spyros, the floor is all yours.
Great. Thanks a lot, Alan. Okay, welcome everybody. Welcome back. I hope the energy level is not too low, or it's my actually task to raise it. First of all, I want to thank Antoine and everybody here at Montreal for inviting me in this summer school. I have very much enjoyed the discussion so far, and I hope that the next 3 hours together will also generate even more interesting discussions. I think Pascal did a great job this morning setting the stage. So, yeah, so what I'm going to discuss today, and that's the plan for today. I'm going to take a step back compared to what Pascal did. So I'm going to start discussing a bit why machine learning in power systems. And that's also what I would like you to start thinking about, right? Why should we apply machine learning in power systems? In what cases does it make sense to apply machine learning in power systems? And then I'm going to go and talk about the data quality, because machine learning is a data-driven method. Not good data means not good methods, right? Or not an output that does not make sense. Then I'm going to talk about physics-informed neural networks, because power systems are physical systems, so why not actually take advantage of all this information we have? And then I'm going to talk about verification of neural networks. Is this performance guarantees that also Pascal hinted about that we can get with neural networks? And then there's also a few boni, or some bonuses, how you would say it. There is a Google Colab notebook. If you want to play with a physics-informed neural network, that's what PIN stands for there, then we can do that. Then we can talk about graph neural networks, or we can talk about integrating worst-case violations in neural network training. This is, let's say, quite aligned with what Pascal presented earlier today as well. But that's actually a decision for later. We have to see how much time we have, and based on what is more exciting for the majority of you, right? Let me first ask a few questions. So how many of you are actually in power systems? And how many of you are actually have done power system dynamics? Okay, and I guess the rest is more towards optimization, right? How many of you have trained a neural network? Okay, good. So that can help me actually see or discuss a few things. Okay, I have 2 slides about DTU. DTU stands for Technical University of Denmark. And I'm going to talk about our department. The department is DTU Wind. In short, the long name is DTU Wind and Energy Systems. As Antoine said, we're a department dedicated to energy and specifically wind energy. So we have the whole value chain. Okay. We're not organized like an electrical engineering department that has a lot of different, say, fields, like telecommunications, electronics, things like that. We are organized with, let's say, a goal. And the goal is to bring more renewable energy in the energy system. So we have a whole division. So we have 4 divisions. Each one of them is actually about 100 people. One division is dedicated on materials, so how we actually develop the materials necessary for the large or larger wind turbines that are going to withstand all these stresses. Then we have a division dedicated on the design of the wind turbine itself. Now the focus is mostly on offshore wind turbines. Then we have a division dedicated on how we make these wind turbines work together in wind farms, and where do we place these wind farms. And then we come to our division that we are actually the largest one, about 130 people right now, how to integrate wind energy and renewable energy in general into the electricity grid. Okay. So it's actually quite exciting to talk with all these different people looking at the different parts. So we have physicists and civil engineers, sociologists as well, how to make renewable energy acceptable to the wider society and things like that. We are about 450 employees in the whole department. We have a lot of collaboration with industry, so 70% of our funding involves industry. We have 280 industrial partners, and we're considered the department in the world that collects the most citations when it comes to wind energy. So there's a lot of work that we do in wind energy, and there is a lot of influence from our department to the world. Okay, so just say a big thank you to a number of people that have actually contributed to the work I'm going to present. Not all of them will have contributed to what I will present today, but this is the team that actually has helped us and our group deliver, or me being here actually talking about this, right? And of course, a number of international collaborators. This work is also supported by the European Research Council, which is, gives out this kind of prestigious grants for this kind of, they call it groundbreaking research. So let's see if this is it or not. Okay, I'm now starting. What we're going to talk about today is actually machine learning power systems. And if you check reports from, let's say, big consultancies, AI and energy are two of the sectors that are going to, or have the largest growth potential worldwide. Okay. So we're actually, separately, AI is going to have is having a big potential, and we see actually its impact already. Energy is something that's going to be very important, already is, in the society. If we combine both, then what do we get, right? The first question for you is, why shall we apply machine learning in power systems? How many of you are applying, how many of you are applying machine learning in power systems already? Only one? Two? Three, okay. So why shall we apply machine learning in power systems? Yeah. To accelerate the simulations, right? So speed could be one. And actually, that's what we saw with Pascal today, right? So it can be much, much faster. Yes, so speed is one. Other ideas? Yeah. The ability to ingest a lot of diverse data. Indeed, it can handle a lot of different data. And that could be something that maybe conventional methods cannot do very well, or require actually maybe a lot of setting up. Others? Yeah. When there are no good physical models for a problem, yes, then this could be something that the machine learning can actually learn some model. I would say not good physical model, I would say there were no models. So when it's possible to model something, right? Yeah. Other ideas? Good. I think, to be honest, yeah, please, go ahead. Stability in power system? How do you mean that? Machine learning can what? Improve stability in power system. And why can conventional methods not do that? So it's possible also with conventional methods to improve stability, but maybe machine learning can do it more or better. Yeah. We will see about that, right? But motivation is key. And so if you see the literature, there's actually a lot of papers applying machine learning in power systems. There is not always a solid motivation. And when we want to actually apply it, then there should be a solid reason why. Not just to replace a conventional method, but actually go beyond a conventional method. Okay? And that's important. To be honest, what you have said actually is also what I have thought. I don't have something extra. Here I have tried to collect it. As you see, we have speed. Machine learning methods can be extremely fast, and that's something that we can take advantage of compared to conventional methods. Machine learning methods can handle well extremely complex systems, so they can ingest all different types of data. This kind of complexity that's not easy to capture maybe with conventional models. And then they can also infer from incomplete data. Okay? And power systems have all these characteristics. There is a but, though, right? There are barriers. So what are the barriers? So when we're talking about power systems, we're talking about a safety critical system, right? If I go and apply something in the control room, who is going to trust that this is going to do a job that's not going to lead a blackout? Blackout means lives, human lives in danger, millions in economic damage, right? And disruption. So if I deploy something in a safety critical application, I need to be extremely sure that things will not go south. Okay. And this is a black box. So why would I trust a black box, right? This is number one. Second, for the ones that have already trained the neural network, how do you test the performance? How do you test the performance of a neural network? Test cases? True test cases? What actually does this, yeah? Diversity of? Of metrics. Diversity of metrics in different test cases, yes. Very good. The standard way, right, this may be a bit more advanced than diversity of metrics. The standard way, what you learn at school, is accuracy. That's the first metric that you get. So you have a bunch of data, test cases, samples, that you pass them through, and you measure the accuracy. The accuracy on this test data is a purely statistical metric, right? There's no guarantee that if the accuracy is 98% on this test data, when I go into a real world, I'm going to have the same performance. It relies on me to pick a good test database or to have a good test cases that reflect reality. And many people tend to forget that. Okay. I don't think that people actually that go into the real field actually forget that, but in the literature, you can design a test case that performs really well, but this test case might have nothing to, not test case, test data set, might have nothing to do with the reality. Okay. So I will not trust something necessarily that is just statistical performance if I don't know, if I have no guarantee or let's say good insight that this is also what happens in reality. And finally, and that's what you get also from a lot of operators, is why would I go with AI? I have spent decades developing good physical models. I trust my models. I have validated them. Why should I now go something completely data-driven? Okay. These are just some of the questions that people will ask, or people do ask. And if we want to apply AI, we have actually to overcome these barriers. Or that's the way at least I see it. Okay. So solid motivation and takeaway number one from, let's say, the talk, or this talk is, if you wish to apply machine learning methods, you need to develop solid arguments. Why, right? So can we discuss a bit when? When shall we apply it in power systems? So what do you think are good use cases? Yes. Forecasting, yes. Machine learning for forecasting, excellent, yes. Why is that a good use case? So we have a lot of historic data and we can use it to train, right, for forecasting. Indeed, we have a lot of data. And what else? Indeed, it's not critical in the sense that it's not. It's just a forecast at the end. And there are actually either the physical models they are extremely complex, or it's impossible to capture all this complexity with a physical model, right? So the forecasting is something that you cannot. There's no benchmark. You can do as good, and maybe you can do better. And that's where maybe AI comes and can improve things. Alex, you want to say something? We're replacing a linear regression model with? Okay. So the current models are linear regression, so AI might come with something better in nonlinear and then can do better forecasting, indeed. What other use cases? So at some point, decision making, so here AI for decision making, when you have a diverse set of data that you need to take into account, and maybe your models cannot actually capture that. Indeed. Others? Yeah. So machine learning for planning, if you have time to validate the solution of a complex problem, how would you do planning, or why would you use machine learning for planning? So the system might be too complex, and then you might not be able to get a good solution, so machine learning can help you give a hint or an idea about the solution, and then you can validate it. That's what you say, right? Yes? Okay, very good. Other ideas? Yeah. First you, yeah. So predictive maintenance and fault detection, very good. Yes, predictive maintenance, it's actually already a use case that's been used. Fault detection, why not with conventional methods? What if it doesn't capture the fault? Yes, so maybe it's better to capture the fault, but if it doesn't capture the fault, you have a, yeah. So, yeah, very good. For what application? Real-time applications. Yeah. Yeah, it's actually very similar to the speed, right? So when we want to speed things up, then maybe machine learning could be something in real time is exactly where we want a very fast solution. Very good. Yeah. Very good. Okay, I tried again to collect this, at least in my view, and I think it actually fits quite well. The way I would describe it is first, when it's impossible, when we have no other option, right? Forecasting, we have no other option. I mean, there are different methods, but there is no conventional method based on physics, if you want, that can actually perform super well. So forecasting is one. The other is when, for example, it's a too complex system, and let's suppose we want to run an optimization, and this is intractable. Very large system, too much data, too many different parameters, too many variables. If it is intractable, then maybe AI can help, okay? And maybe AI can help in a way that can give some guidance, a warm start, or it can give, let's say, or decide the active set, so what are the active constraints, or exactly as, yeah. And what Pascal presented is actually about speed, and that actually is, for me, the second family of methods. So when we want to speed things up, maybe that's a way to do it. Okay. And again, that's how I interpret things. It's not necessary that it's the only way to interpret things. Okay. What is the added benefit with machine learning when we already have a method, right? For example, we can have these very complex optimization methods, a mixed integer linear program, or mixed integer nonlinear program, which is actually the most difficult one to solve. Then maybe AI can help. If we develop solutions, the machine learning method can run on a laptop. We might need a supercomputer to train it, but once it's trained, you can deploy it on laptops and get, let's say, a close enough solution, as Pascal also presented. Okay. So that's one of the benefits. You don't need every time to have a kind of very good computer, or in some cases, supercomputer, to run these methods. Very good. Now, how do we overcome these barriers? And that's what I'm going to talk about today. So first of all, data-driven methods, we're talking about garbage in, garbage out. How do we improve the quality of the data we train on? Okay. So I'm going to discuss a bit about some of our ideas on how to create or to efficiently create databases for training. And I will discuss also why, for some methods, we need database, because data is actually not always enough. Then I'm going to discuss about performance guarantees, and this is verification of neural networks. And I'm going to discuss about physics-informed neural networks, where we take advantage of the models that we have already developed in order to design AI tools that can be very, very fast. Okay? Very good. So I already talked about this. So let's, I know that or I saw at least that several of you have experience with training neural networks. I will have a very short overview and an example. I will use example because I'm not so sure if everybody's aware. If you think that's trivial, then we move on, okay? So what do we need to train a neural network? Most of machine learning methods, but let's now focus on a neural network just to, let's say, have a concrete example in our head, right? I need data. I need a training database. I need a training algorithm. This can be, let's say, the Adam optimizer or anything that I am going to use in order to fit the network on the data. And I need a test database, okay? For the test database, usually, I mean, how things are, this is split. Let's say 20% of the data is for testing, 80% is for training. Sometimes it's 10%, 90%, depends, right? The modern toolboxes actually split that themselves. So you just actually enter the data, you decide the network that you want to build, and then everything is done in the background. What I said before, and I just want to stress, it's very important that this data represent or reflect reality, okay? Because at the end of the day, the performance we are going to get when the training ends depends on this data. Very good. I think it's the third time I'm saying that, so I think I'll just leave it here. Okay, I think it's quite clear. Let me actually give you an example, okay? So there are different metrics, as also Francois mentioned. The most common, or at least in the past, the most common was accuracy. What is accuracy? I have, and now we're talking about neural networks for classification. I have two classes. Let's suppose that I'm training to understand if a system is safe or unsafe. So if a power system is going to black out or not going to black out. So I have a lot of operating points. These are labeled operating points. I train my neural network on these points, and then I want actually my neural network to very fast tell me for every new operating point it gets, if this is a critical situation, should I do something, or I'm safe, don't do something, okay? Now, when you train, then there's definitely going to be some mixed classifications, at least at the beginning, okay? And probably always. So what is misclassification? Misclassification means that I have my true positives. These are, let's say, the system is safe, and my neural network says it's safe as well. But then I also have my false negatives, where the system is actually safe, but my neural network says it is unsafe. Okay, so that's a misclassification. And the other way around for the unsafe class, where we have actually the true negatives, so this is truly unsafe, but there is also some that were misclassified as safe. And these are actually the most critical ones, okay? Now, let's assume I have only 1,000 data points, just for the sake of example. 5 balanced data set, 500 safe data points, 500 unsafe data points, and I train, and actually that's what I get. I get 480 correctly classified as safe, and 20 misclassifications. 470 correctly classified as unsafe, and then 30 that were supposed to be unsafe were classified as safe, right? What is the accuracy on that? If somebody has a calculator, can do that. 95%, okay, very good. Okay. Now, let's suppose we have a different data set. Now, my data set, I was only able to collect 20 safe points, and I have 980 unsafe. And actually, if you see the input region, so all the permissible space of the generators, 90–80% of that region is actually unsafe. It hits some constraint. It can be generator constraint, voltage constraint, line flow constraints, but actually it's only usually 2% of that space where we're allowed to operate. If you consider that I'm having a generator, let's say from 0 to 100 megawatts, let's suppose I have 10 of those, so think of 10 these dimensions, I'm only allowed to operate in a very small region, right? So if I sample naively over this whole input space from 0 to 100 to the 10, then I will only collect 20 safe points and 980 unsafe. And then from the 20 safe points I collected, I have misclassified 19 as unsafe. What is the accuracy here? Who said, what's that? Slightly higher, yeah, 95.1, yeah, but 95%. It gives me 95% accuracy, which should make me probably happy, but I have misclassified 19 out of the 20 points that were actually safe. Okay. I just want to make the point that seeing a number at the end of your neural network training does not mean much if you don't know how to interpret that. So what do we do here? Yeah. So we could see separately for each class, for the safe and unsafe points, that's what you're saying, how well we do, right? Yeah, very good. That exactly brings me to the next slide. We need to use, when we're talking about classification, we need to use a diverse set of metrics, okay? And that's where actually recall comes in, that's the true positive rate for the specific class, or specificity, and so on. So one metric is not enough. You should make sure that you have assessed a wide range of metrics as long as you have no other means to do, let's say, validation. If it's only statistical, take a range of metrics. So this is, for example, for one of our works, we try to do something like this, like a spider diagram, where you try to assess across a number of metrics. Okay? And there's a wide range to pick from. Good. That's something I hope that you can take home with. Some more, at least for the ones that have not tested or have not struggled so much or spent their lives working with training, neural network training. So first of all, regularization is very important. It helps a lot for a neural network to perform well if you normalize. Okay. So instead of having, let's say, 0 to 300 megawatts, try to normalize it between, let's say, 0 and 1, and all your inputs. Because it's, at the end of the day, neural network training is an optimization. Every output is actually on the objective function. If the outputs have different units, if one output is, let's say, around the thousands, and the other is around the 0.1s, it will heavily be directed the solutions toward the thousands, right? So you need to somehow normalize them to have an equal weight. Then one-hot encoding when it comes to classification helps a lot as well. So instead of having, let's say, an output that is 0 or 1, signifying that 0 is one class, 1 is the other class, then it's better to encode that as what's called one-hot encoding. So you have two outputs for every class. It's 0, 1 if it's one class, 1, 0 if the other, right? So here, let's say, instead of having unsafe equal to 0, I have 0 safe, 1 unsafe. This helps helps the classifier, or helps your neural network train better, to have two outputs instead of one for this kind of binary classification. Okay, a few more takeaways. So if you do classification, make sure you have a balanced data set. If you don't have a balanced data set, it can have a detrimental, let's say, a really bad effect on your training, right? You're not going to do well. Or not as well, at least. Accuracy is not sufficient to assess the performance. Make sure you use a diverse set of metrics. And then people that have actually trained neural networks, they know that they have to spend a lot of time and do a lot of tricks. It's an art, to be honest, on how you can achieve a good, a well-trained network, right? To do what you wanted to do. And I think this was also the message from Pascal, saying how many times they have failed until they actually succeed. Okay. Great. Now, so for the remaining. So I'm going to split that in 3 parts, ideally with a, or not ideally, with a break in between. So I plan to spend, let's say, 45 minutes. So let's say that for the next 15 minutes, I'm going to talk about generating or efficiently generating a database. Okay. So we were concerned with this task of how you generate a good database in order to train for classifying if a system is secure or not secure, right? And why is that? First of all, we did not have access to real data. Second, even if we had access to real data from an operator, there are very rare the cases that the system is insecure, and very often the system is secure and not close the boundary, right? So our database, even if we had real data, it will not be, let's say, good enough to cover all possible cases. We definitely need simulation data to be able to capture all the possible cases so that we have a classifier that when we enter a critical condition, it can truly understand it's critical, right? If I train on a database that 99% it's safe, because that's how power systems operate, then I have major concerns if I'm really going to detect an abnormal situation. Okay. So we need this kind of synthetic data or simulated data sets to be able to train this kind of classifiers. So if you try to do that, it's a very complex task to generate a database, right? So we try to see how to do that more efficiently. So we came up with an algorithm that is, we consider it's modular and highly efficient. It can accommodate a lot of different definitions of power system security, N-1, N-K, small signal stability, voltage stability, transient stability, or a combination. From what we have seen so far, it's 10 to 50 times faster from what existing state-of-the-art approaches are. And in our case, or what I'm going to show, and the toolbox that I have online and you can use, and I have a link later for that, is N-1 security and small signal stability. Okay. So let's see what we try to do here. So we started with a steady state, and this is actually the feasible domain. Okay. So if we go back to optimization, this is actually the safe region, so where all voltage and line flow constraints are actually satisfied, and this is the unsafe region. That if we suppose that these are, let's say, 2 variables, like 2 generators, this is from 0 to 100, if you want, or 0 to P max of each generator, and that's a 2-dimensional projection of this feasible space. Okay, it's a non-convex space. If I do this kind of uniform sampling, then as I said, I will actually, it will take me quite some time to be able to sample both safe and unsafe points. So how can I do that efficiently? Our hypothesis was that we really want to focus on the security boundary. So the idea is that if I'm able to focus on this boundary, both from the inside and outside, and generate a lot of data around that boundary, I will be able to train better models, right? Better neural networks or better decision trees. So what do? I define this kind of region. This is now a true safe region of the 14-bus system. It's the projection in 2 generators, P1 and P2 of the 14-bus system. And that's actually the true safe region, and all the rest is actually unsafe, right? And I define this high information content region that's actually right around it. And I want to focus on that to generate as many data as possible around that region. Okay. I go with convex relaxations. So here's what I do. I convexify this feasible region. I get a convex relaxation of that with an SDP, so semi-definite programming. I formulate an SDP. And I draw a random sample. Let's suppose that I draw this unsafe random sample. I solve an optimization problem. I find the minimum distance that satisfies the convex relaxation constraints. And I draw a ball around it. Okay. The moment I draw a ball around it, then it's guaranteed that all these points are actually unsafe. I don't need to sample anymore in these regions, right? It's guaranteed that it's unsafe I can go on, and that's how I can quickly create this kind of regions and move on. This is now an actual illustration from the 14-bus system. Again, now these are in a 3-dimensional space, 3 generators. Again, it's a projection because we have in total 5 generators for that, and if you go to bigger systems, it's much higher dimensions, right? So it's a projection in 3 dimensions, and you can see the different balls that we generate, right? Which actually I find it a nice figure. And then what did we do? We actually went a step further with our friend and colleague Dan Molzan. So instead of actually drawing the ball, we drew hyperplanes, and this was actually much faster. Okay. So instead of actually drawing the ball, I have the minimum distance, and I draw the hyperplane perpendicular to this vector, if you want. Then I can very quickly discard a lot of unsafe space, and then I can focus on this convex relaxation and try to sample in there. Okay. So after I do that, then the magic, so to say, finishes. We still have to see what else we can do to be faster. But what we do after that is then we sample inside this region, and we go this kind of direct walks. This means gradient descent. If I am somewhere here, I go with gradient descent towards the boundary, and then I try to traverse this boundary. So I'm moving along the boundary. Okay. If I randomly sample from the inside, I'm doing the same thing. I'm going close to the boundary, and then I'm trying to do that. What is a boundary? For me, the boundary is the power flow constraints and the small signal stability. To be something small signal stable, it must have 3% damping ratio. If this tells nothing to you, it's just, let's say, another boundary. It's how damped my system should be in case I have a small perturbation, to make sure that it will, if I am here and I do a small perturbation, I want to be sure that I can go back to my stable equilibrium, right? And if I'm adequately damped, I'm going to do that. If my system is not well damped, a small perturbation can actually get me somewhere that's unstable. So with 3%, it's let's say, one of the indices that a lot of power system operations use. You can actually go back to something that is stable, and that's what we use. And that's what we saw here with this kind of direct walks. It's nothing else than a gradient descent method to go to the boundary and try to focus and generate as many points along the boundary. So some results. For the 14-bus systems, we're able to actually generate with brute force the complete security boundary, right? And it took us 10 hours, 556 minutes. It took us 10 hours to be able to map the complete security boundary. We compared that with importance sampling. Importance sampling was actually able to do that in 37 minutes. And the method we propose here is actually 10 times faster than that. Okay. In the 162 bus, it's impossible to track the complete security boundary, at least in the time we have available. The importance sampling, so you can understand that the moment we go to larger dimensions, this actually grows exponentially, right? It's a huge problem. The importance sampling method was able to do 901 points in 35 hours. We're able to actually collect 180,000 points in the same time, approximately. Yes? So the question here is if this stability boundary is for any type of stability. This stability boundary here, well, as we said, is for steady state, n-1, and small signal. Nothing more, right? So that's what we have here. It could be more, but yeah, then people need to implement that. So the question is if you have already a framework to characterize stable and unstable cases for transit stability, if this can work. I think yes, because actually the main idea here is that we accelerate the steady state part, right? And then as long as you are in, say, steady state, then you have this framework to have transit stability So then it should work with a gradient descent method, this kind of direct walk. Yeah. Okay, so make sure that I have my microphone closer to my mouth. So what I'm going to discuss, because we revisited that actually this or last year, and we had a paper this year. This is an open source toolbox. You are welcome to actually download it and use it. It's also on the slides online. And generate your own databases for any system that you want. It's implemented in Julia using parsem.jl and all the, you can actually, there's a huge database, it's a large database of systems that you can use, or you can enter your own system. What I'm going to discuss here is I'm going to compare the Latin hypercube sampling. This is uniform sampling across the area with important sampling and our method for two systems, the 39 bus system and the 162. Yes, question? Go to the next or previous? Yeah. If it takes a different distribution of what, this method? I don't do probabilistic. So the question is if it considers different distribution of data, this method, but I don't do probabilistic. I sample, I just need to find the true security boundary, right? I don't, it's not in my interest to find, let's say, what is most probable to happen. Of course, if there is high probability and you are interested in this kind of data, then you can use a probability distribution as a prior to start sampling around that area, yes. But for me, I really want to understand what is the true security boundary of the system. That's what I want to map. To be honest, if I sample that and I train a good method or a good model on this, then I can use this distribution to see how safe they are. Okay. Good. Now, some results. You can see that all three methods, so this is a Latin hypercube in blue, important sampling in red, and yellow, this is the proposed method. They do generate more or less a balanced data set, which is good. The method that we propose, as expected, if it didn't actually, then we have failed. It does generate a lot more data in this high information content region. This is exactly around the security boundary. Okay. Now, I just present here, we have a lot of different graphs. Let me present just one. For the 162 bus system, I have again a 2D projection. These are like the projection in 2 dimensions of two generators, the generator 10 and generator 12, how the sampling takes place. Okay. You can see that the Latin hypercube sampling, it actually samples all over the whole region. Important sampling, it's a bit less crowded. Here it's actually more crowded towards the security boundary, as it should be. With the method that we propose, we actually have, it's 2,500 times reduction in the input space. We don't sample at all in this space that we know it's unsafe. Okay. And it might not look like 2,500 times, but this is just a projection, right? So if you imagine the full dimensional space, it's that much. Now, on the right column, I have how many of these points are in this high information content region. This is around the boundary. So you can see that all of them managed to get some around the boundary. The proposed method, as expected, actually gets more. Okay. But what is very interesting, at least for us, is that none of them was able to capture the full security boundary or to capture at least a superset, right? This actually talks about the complexity of the problem and that there's also more work to be done. Computation time, right? We had different computation times. Let me just mention this. So to generate 1,000 points in this high information content region, with the proposed method, this is about 50 times faster than the standard uniform sampling, okay? And about 2 times faster from the important sampling. Here, for the largest system, this is about 16 times faster for the important sampling and 74. So if we have this kind of methods, then we can actually, we use the knowledge or the knowledge of the physical system to generate data that theoretically should be carrying more information for the training of our models. And that's very important. to find ways, and that's only an example, right? Think about your problem, think what data is going to be the most helpful for you, and how you're going to generate them. Don't just generate without, I don't know, without trying to be a bit smart, because actually it might take forever, or you might not be successful, okay? Now, the question is, how important is this high share of high information content samples for the training of decision trees? What we did here, of course, you can also train whatever you want. We did decision trees because actually it's simple to train, and we can, let's say, we have a better intuition of how things work. And here I have just the F1 score. You don't need to know what F1 score is. It's just a score. But if you are curious, then this is the explanation. So what we did is, and that's actually now a bit tricky, we trained decision trees with each of the 3 data sets. So Latin hypercube sampling, importance sampling, and proposed method. And then we tested each decision tree for all the other test sets. Okay. So we did not only test it on its own data set, but we also tested how it performs on the other data sets. How well can it actually, because at the end of the day, it's the same system. They should be able, these are all data that should be able actually to tell if it's safe or unsafe. And these are the results now, right? So here's, we trained with LHC, we tested with the same data set, we have 98 or 0.98 F1 score. We tested with importance sampling, we trained with importance sampling, we tested with importance sampling, 92.92. And the same with the proposed method, you see? So as you see, each method, for the data set it was trained on, it had the highest performance if it was tested with the data generated with the same method. And it did worse with the data set trained from all other methods. Why? Because it's a different distribution of data. And that's important to keep in mind. Okay. Now, what we also did is we took data, 10,000 data right around the boundary. And we tested each of those methods. So these are separate data around the boundary. The proposed method actually is about, let's say, 10–15% better than the rest in terms of F1 score. And if you see here, it's also on average, performs very well on all data sets compared, let's say, to the LHC for the importance sampling or the importance sampling for the proposed method, right? So in general, it had a more robust, if you want, performance. I wouldn't say it's, let's say, it's out of this world, but it is an improvement that's actually, I would say, significant. Okay, and that's, at least in my opinion, that's how one should actually go about this kind of methods. You need to be able to test in different data sets to make sure that your method is robust and not just, train with your data set, then test on your data set. Oh, I'm good. I'm 98%. No, you're 90. No, okay, it's not 98%, but I'm 0.98 here with LHC, and then I'm actually doing really bad on the boundary. And that's the same system. It's exactly the same system. Final slide, balanced data set or unbalanced data set. So now we only focus on the method we discussed. We generate 10,000 points randomly across the input domain, and then 10,000 points, making sure that we have 5,000 in the safe region, 5,000 on the unsafe region, right? And we trained for that. And you can see that when the data set is actually balanced, it performs better on all different data sets, and significantly better at the boundary. For classification methods, it's very important to have balanced data sets. Okay. Good. And I will close with that before going to break. So we need balanced training data sets, and creating this kind of high-quality data sets that are important to train good models, it's actually a very complex task. And an open research topic, right? So this is some effort. There's an open source data set or toolbox that you can use, but there's a lot of work to be done if you really want to train, then also to be successful at training. Good. Okay. So what's the challenge? And here I have actually an example from Australia. Why do I have Australia? Because for that system, I know how long it takes to simulate. So assume we want to operate, or we operate the Australian grid, and we need to eliminate the blackouts for the next day. And we need to perform simulations, right, to see what the risk is. Now, if I want to simulate 20 seconds of the dynamic behavior of the Australian grid, I need 12 minutes with the recurrent tool. How much does Quebec need? Do you know? I don't know. How much does a dynamic simulation on the Quebecois grid? Yeah. So RMS simulation, let's say this phasor mode simulation for 20 seconds, or I don't know how many seconds, yeah. Now, with your tools that you have right now, how long it does, I don't know, but how long does it take? A little bit slower than real time. Okay, that's actually quite good. But the Australian, actually, they need 12 minutes for 20 seconds of simulations. Now, think about that we have hundreds of nodes, right? There are thousands of potential contingencies and a lot of operating points that appear during a day, right? We're talking about millions of scenarios that actually need to be simulated to make sure that we are safe. So can you imagine how much time this is going to take? So here I just have an example, 100 most critical disturbances over a day for 5 representative operating points during the day. It requires 4 days non-stop simulations based on this data, okay? To do that every day, that's impossible. If I need 4 days for every day of, yeah, that's actually not going to work. If I'm able to accelerate that by 100 times, I will only need 1 hour. So I can bring this down from 4 days to 1 hour. So the question is, can we do 100 times faster? And if we can, and how actually, right? So my goal is to bring this down to 100 times faster. And my hypothesis, if you want, is that conventional methods cannot do that. I need to think differently. I cannot just improve an existing method and be 100 times faster. I might manage 2 times faster, yes. But I don't know how, yeah. So that's why we're thinking about physics-informed neural networks. So what is the benefit, or what the benefits that we see with physics-informed neural networks? First, why are they faster? Maybe let me go back. Why could neural networks in general be faster than the conventional methods to perform dynamics? So Francois says that if you run the algorithm on a GPU, you benefit from the architecture. So if you run the machine learning or all of them, or both. True. I can tell you that also there are some experimental approaches to run also the conventional methods on GPUs. That is also faster in GPUs. But let's say that they are both on CPUs. Let's suppose that, yeah. You are computing a fixed set of computation instead of searching the whole space. No, it's not about searching the space. Yeah. A lot of operation with machine learning is done in parallel, while numerical solvers or conventional solvers do that in parallel. That is true, but let's suppose that I have CPU, one CPU, one core. So I want to be equal, right? I don't want to take advantage of other tricks. Yeah. Simulation might be nonlinear, so you might need iterations. to find the solution. Yeah, while? Mm-hmm. A neural network? So you are representing the neural network, you are representing the system with a neural network, so it's linear relations, which means? Which means you only need one go, right? And actually, that's exactly what it is. So dynamic simulators, so we're talking about nonlinear systems, okay? Nonlinear differential algebraic systems, this actually just fancy words. It's a nonlinear system that we need to solve. There is no analytical solution for these systems. Any solver you are going to use, it's a numerical solver that will do iterations, right? Newton-Raphson, Newton solver, whatever, is going to iterate, and that goes step by step, will converge to a solution with guarantees. It is guaranteed to converge to a solution most of the time. Okay. What does neural network do? I am training to infer the solution. Okay. It is an approximation, an inference, but if I do my training well, then it's a single step. I just ask my neural network, tell me in a second how much will my power, my frequency will be, and the neural network will tell me. Okay. If I've done my job very well, it will tell me with high accuracy without requiring to iterate over it. Okay. What do I actually do? As Pascal said, I offload part of the computational task in the training so that it can be really fast in real time. Okay? But that's the main idea. The main idea is that I can be really, really fast because it's just a matrix multiplication. It's nothing else in the neural networks. That's number one. So neural networks can be faster because of that. Number two, why physics-informed neural networks? And I know that we haven't talked about it. Maybe some of you have worked with that. What is the benefit of physics-informed neural networks compared to conventional networks? Yes? You can have meaningful parameters and constraints. Yes, in terms of constraints, I guess you mean that I can include my physical equations in there. You can, yes. Yes? Physics-informed neural networks require less training data. Yes. Yes? You can get some guarantees for the behavior you want with physics-informed neural networks. Actually not. Yeah. You can penalize, so you can drive your neural network towards something that makes physical sense, but there's no guarantees in the standard form. Okay. Good. The main advantage is less training data. Okay. And we're going to see why, but actually what happens is I don't need to have large training data sets. I have my constraints in my neural network. I randomly generate samples, and these samples, when they go through the neural network, should also validate the equations that I have in constraints. It's like a constraint optimization, right? The output of the neural network should also satisfy the equations that I have in my constraints. As long as it does, it means that this physically makes sense, and I am training or I'm fitting a neural network to comply with a physical reality. I don't need to generate thousands of trajectories. I just tell the neural network, fit a model on this physical representation. Okay. And this training takes longer than a conventional neural network. So if I have a lot of data, it's faster to train a neural network than do a physics-informed neural network. Why? Because I have to consider all these constraints, and I have my optimizer to take into account all these constraints. Anybody that has done optimization understands that, I hope. It's the same thing. But it's much faster if I consider the time that I need to do for generating the trajectories or the data myself, right? If I don't have data, or if I don't have enough data, and I need to generate data in order to be able to train on them, it's faster to do a physics-informed. And that's why, for us at least, it makes much more sense to focus on physics-informed neural networks, or pins. I'm going to start calling them pins, if you don't mind, for dynamics. Because generating a trajectory in dynamics, if it takes me 12 minutes to generate a single trajectory, and I need, I don't know, 1 million of them to be able to train on them in order to infer then if it's safe or unsafe, then I've lost the whole game, right? I want to be faster, so I just can include the equations in my neural network and then train on them and create a model that's equivalent that I can then infer. And we're going to discuss about how this becomes scalable, because what I'm saying right now is not scalable for the Australian grid. But we have actually solutions on how this scales. Okay, questions so far? Is the main idea clear? Okay, yeah, okay. Good, so this is exactly what I discussed. What's the benefit of pins and why are neural networks faster, okay? Now, I'm starting with the basics. Just I hope you bear with me because it makes a good connection, and I just want everybody to be on the same page. Neural network training is nothing else than an advanced linear regression. It's a non-linear regression, okay? So let me use this example of linear regression to talk about neural network training, and then I will go to physics-informed, and that's what I want to explain, okay? So what is linear regression? So I have a bunch of data, and I want to find a line. What is finding a line? I want to find the coefficients W1 and W2 that actually minimize the distance between the line and all the data. What's distance? Mean square error, for example, okay? How do I formulate this problem? It's an optimization problem. Minimize the distance between the y. The y is my actual data, and y hat, this is the estimation from my line. What are the variables, optimization variables? W1 and W2. So find the line so that y hat is equal to W1 plus W2 xi. Okay. So I have a random input xi. I get it through a W1, W2. I have a y hat, and this y hat should be as close as possible to the true yi that corresponds to xi. Okay. That's linear regression, and that's also neural networks. Now, instead of these coefficients, think of W1 and W2 as the neural network weights. It's exactly the same thing. Okay. It's not a line, it's something more advanced. Good. Now, what happens? So we have now automatic differentiation. This is actually something that's already included in all actually neural network or machine learning training platforms. And what this gives us is it gives me a derivative of the output of the neural network with respect to an input. Okay. Why is this cool? You can do a lot of cool things with that. For me, this is cool because I can have differential equations as constraints. Because I can compute not only the output of the neural network, but also the derivative of the output with respect to input time. Okay. So here's now how this works. This here is the original loss function. So if I was training a neural network, I would generate a lot of constraints. I will generate a lot of trajectories, I'm sorry. So this one trajectory, I have an initial condition here that I start from here with, let's say, p equal to 0.17. This doesn't make any difference. You can consider that as an initial condition. And then I want to see how my rotor angle and my frequency here evolves. So I generate all these trajectories, and I have all this delta and delta dot, because omega here is the frequency, which is the first derivative of delta. And I train on that. So I sample these trajectories, and I train on all this data. That's what I would do normally. Get the trajectories, sample them, train on them. Now, what am I doing instead? I'm adding this regularization factor here, which is nothing else than the following, right? I get the output of my neural network. This is delta hat. Okay, that's my inference. I take the first derivative of my output and the second derivative of my output, and I plug those in this equation. Okay? So I have an input P, and I have a time T that I don't show here for convenience, but actually that's for specific time T. I have a delta dot, and a delta double dot. I plug them in this equation. These are all outputs of my neural network. And they should actually get this f of delta to 0. How will they get this f of delta to 0? By changing my weights. So in every training iteration, I change the weights of my neural network. So for a specific PM and time, then this is equal to 0. The moment this becomes equal to 0, I comply with physics. I comply with the physical world. Okay. And I have done what? I have actually fitted a neural network to be exactly following these trajectories without generating any of the trajectories. Is that clear? Questions? Yeah.
You are using the trajectories and the time samples, right, for this data to fit it in?
I use very few of them.
Okay. And you somehow preserve the ordering sort of because there's a time dependency, right?
So time is an input. So for every time, I should be at a specific point in my trajectory. So this x-axis is time, right?
Yeah.
Here we had, what was that? Oh, I'm sorry, I'm going back forward. Here I had x and y. X is my time, so it's my input. And then I have a third dimension that's actually p. I don't need an order anymore, right? Because even the equations will tell me that for this specific time, this is where omega or delta should be.
So, interesting. In these contexts, or is it jumping the gun? What happens if there's like a discrete change, for example?
Great. That's a different question, yes. If we have a discrete change, then we have to consider that. But this actually changes the equation. Right? So this equation has no discrete variables in here. There's nothing discrete. This is just a physical evolution of delta and omega with no discrete event taking place.
Yeah.
If there is, let's say, a change of p from 0.1 to 0.5, I can capture that as long as I have trained for p's between 0 and 1. Right?
So then whatever variation or discrete changes, as long as you capture that in the training, it should...
yes. Yeah.
So if there is hypothetically, let's say, a three-phase fault, or...
You are moving several steps ahead.
Okay.
Okay. But we can discuss this. Yeah.
How sensitive are you to initial conditions of the grid? Because what is the assumption about that?
I need the initial conditions.
So you know the initial conditions?
Yes,
Okay.
yes.
Yeah.
I need, yeah. Other questions? Great. So now, what we think that this can work for, or at least as a first step, is to screen very fast a lot of scenarios in order to select what are the critical ones and then go with a conventional solver to simulate the critical ones. Okay. That's what we see our first application. Of course, the vision could be, or what we would like to see, is a solver based on pins. That's actually the main tool to be used, right? But this will take a lot of years and effort to get this accepted, right? For now, we just want to focus mostly on screening very fast. So in this very simple example, the pin is actually 87 times faster than the ODE solver. We are solving a single differential equation, right? And we can be 87 times faster. And one of the benefits is that I don't need to integrate. Let's say I want to determine what will be my omega at t equal 10 seconds. With a numerical solver, I need to go and integrate from 0 to 10 seconds in order to figure out what my frequency will be. With the neural network, as long as I have actually trained for this period of time, I just ping it or poke it, whatever you want to call it, ask it what is the frequency at t equal 10, and it will just spit it out. Okay, because it does not integrate. It has learned that. Good, and then we have actually done quite some work in this, testing different things. So here now we have trained a single pin for a whole system, 11 bus and 39 bus. Okay, and we compare the speed and accuracy. Here it's actually the speed of each of those options. So what do I show here? Here I show on the x-axis, it's logarithmic, by the way, the prediction time. So how far ahead do I want to predict what the omega, so the frequency will be, the rotor angle will be, or other variables, right? So I'm predicting that. Maybe in 1 second, after 1 second from now, or in 10 seconds and things like that. And then what I plot in the y-axis is how long it takes to compute that value. And obviously, so here what we have, it's a clear separation between the conventional solvers and the physics-informed neural networks. What is interesting here is, obviously, if you want to predict what's going to happen in 10 seconds, or you want to evaluate what's going to happen in 10 seconds, then the conventional solvers take longer because it takes them longer to integrate until that point. For neural networks, as long as you have actually trained them for all these 10 seconds, then it's exactly the same time. There is no impact of the prediction time, right? That's what we said. It's direct estimation. Now, for these systems, we see that there is an advantage of 20 times to 1,000 times between the minimum and the maximum here of how much faster the pins could be. Single neural network for a whole system, right? But there is a trade-off. There are several trade-offs. So the first one is, the further ahead we look or we want to predict, the more time it takes to train. And I guess that makes sense, right? If I want to predict for the next 10 seconds, then obviously I need to have a lot more data to train on for 0 to 10 seconds for a lot more initial conditions. And pin accuracy drops. At some point, it becomes intractable as well, right? It requires too much. So what do we do? So what we decide to do is to form this kind of recurrent pin, if you want. So what do? We don't, let's suppose that I want to infer for 10 seconds, right? I don't train for 10 seconds. I train for 1 second, but for all possible initial conditions. Okay. So I train for 1 second. What do I have here? I have 2 seconds here. Okay. I train for 2 seconds here. So I ask my pin to estimate or to tell me what's going to happen after 2 seconds. I take that output, plug it back into the pin, tell me what's going to happen in 4 seconds, take that back in, what's going to happen in 6 seconds, and like in 5 times, I have actually estimated what's going to happen in 10 seconds. Okay. What do you think are the challenges with that? Or what do you find that what could be problems with that? Yeah, compared to single pin, yeah. The question is what happens with the control actions. We don't consider that this yet here. Okay. This is a separate, then we're talking about also discrete or other kind of events. This is just the physical evolution of the system. That's where and then we will go there. Or we will discuss it, I would say, yeah. Yeah. Errors accumulated, very good, yes. Why is there an accumulation of error? Because the moment I infer, I induce an error. There will be an approximation error. There will also be an error in the numerical solver. It's guaranteed to be maybe 10 to the minus 5 or 10 to the minus 4. It depends how much the tolerance that you set. But there will be an error. And if I do this pass 5 times, I accumulate this error compared to a single pin that I don't have this accumulation. Indeed. What else? Yes. Correct, yes. I take the output at t equal 2 seconds, so here, and I plug it back into my pin. I have trained my pin for all these, all initial conditions, so it should be able to capture, it doesn't care, right? I just enter it as a new condition, and let me know what's going to happen in 2 seconds. If I have learned the physics well, it will do it without a problem. So the other issue is a bit slower, right? Because instead of having 1 pass, now I have 5 passes. But it is slower, yes, but still 100 times faster because this overhead that we induce, it's very, very small compared to what the numerical solvers need to do in order to arrive at 10 seconds, okay? So it is a bit slower, but not actually significant for us. Then we have an accumulated error. If we train with high accuracy for this now 2 seconds, which is much easier to do compared to 10 seconds, if we train with high accuracy, then this accumulated error is actually very small. And we're going also to see how this works with the actual simulations, okay? Good. Now, let me see, this works. So we started actually working with some companies. One of them is Ørsted. Ørsted is the largest offshore wind developer, and happens to be headquartered in Denmark, actually very close to our university. So Ørsted builds wind farms, okay? And what they need to do is they need to design controllers that ensure that the wind farm is going to integrate safely to the rest of the system. So here what we do is we are working with tuning a PLL controller. PLL is for phase lock loop. If you don't know what this is, it doesn't matter. We tune a controller. We try to find the region of attraction of that controller to see where is it actually safe to be, or for how many points operating points it goes back to the stable condition. Okay. So normally we need electromagnetic transient simulations to do that. And I guess Jan also talked about EMT on Monday. And we need to perform a lot of different scenarios to start, let's say, from many different initial points and see how this actually converges to the equilibrium point or diverges in order to find what are the best parameters for the controller. Okay. So, and now what we did is, so this is actually training 250,000 points, not training, this is simulation of 250,000 points with EMT, and this is with our physics-informed neural network for different parameters of the controller, or actually of the system. So how the region of attraction changes, right? You see that it starts from quite big, and then as the system changes, then we get to a much smaller region of attraction. This means a lot of more points actually are dangerous, and we need to have a different controller. Okay, so there is no way so far to tell how well our pin does other than inspection. And by inspection, actually, it seems that it's doing quite well. Okay, it's more or less exactly the same region. Now, we did 5 million points. 5 million points is impossible to do, or not impossible. It's possible to do with conventional simulation. It will take you 2 days. Okay, and we did training and evaluation in 2 hours. Training the pin and evaluating 5 million points in 2 hours compared with the 2 days that it will take to do the same 5 million point simulations with EMT. Okay, so this is 25 to 100 times faster. And the benefit is once you train it, once you spend this 90 minutes training, then you can run it on a laptop. Questions? Okay. Now, what can we do with pins, right? First, or what we are looking at least, I guess one can do a lot of different things, is to integrate them into existing simulators. And the idea is to replace the slow components. What are the slow components? There are, for example, inverters that have very fast time constants. Fast time constants means that I need to have a very small simulation step because a lot of things change in very short time. So I need to do a lot of iterations. So small step means a lot of iterations to be able to capture trajectory. If I replace this kind of very fast components with a pin, then I can infer for longer horizon, and I don't need to do these very short time steps. Okay, this is number one. And the other one that we're working on is a pin-based simulator, right? A simulator for dynamics completely based on neural networks. Okay. Let me talk a bit about now, just to give you some background. I guess I'll talk for about 15 more minutes and then we'll have a break, okay? Maybe 10 minutes. I will try to limit that. We use a trapezoidal rule. Also, conventional or commercial simulators use the trapezoidal rule. This is the most common integration method. I don't know how many of you are familiar with that. It's not rocket science. This is a standard differential equation, right? dx dt equals to f. I don't care what this is. What I do with the trapezoidal rule is that this is now my derivative. This is my derivative curve, okay? And this is my derivative, let's say, dx dt at 0, and this, let's say, on the next time step. What I need to find out, if I want to integrate, is I want to find the area under the curve, okay? How do I do that? I approximate this curve with a trapezoid. So here, then a direct line up to here is a trapezoid. If I compute that area, then I have found the integration of dx dt over time, so that's x, right? I want to compute the trapezoid. So obviously, I cannot go from this point to that point because I would have misapproximated or misestimated the true area, but I take smaller time steps to make sure that I capture well the trajectory. Clear how trapezoidal rule works, at least the intuition? Okay. Yeah, small trivia question. Do you know when this was invented? Maybe you can estimate or use your neural networks to generate an answer. Yeah. Ancient Greece? Almost. A bit later than ancient Greece, yeah. 50 before Common Era or before Christ, whatever you want to call it, in Babylon, okay? So we have that around for about 2,000 years, which actually, for me, it was quite impressive when I learned it. Very good. So what are we trying to do now? I want to replace the trapezoidal with my pin. So if you see, I formulate, because now the whole thing or the art is how I formulate my neural network to be able to be integrated into a commercial solver, right? What kind of inputs and outputs I need. And as you see here, two things. First, the colors not seem very well, but you are going to see that I have exactly the same inputs as I have here. So it's exactly the same variables, more or less. There's only one difference. The difference is that my x of t, because I'm trying to estimate what the x of t is, right? Given my xt minus 1 or minus delta t. So my x of t here in the trapezoidal method appears both in here, so on the left side, but also on the right side. My x of t in the pin, the way I have trained it, appears only on the left side. So here I need to do iterations to be able to determine what my x of t will be at the next time step. While in the integration, it's just a single step. Okay. So as long as I have defined my pin like that, then I can actually easily, as long as I have trained it, I can just exchange one inverter, 10 inverters, as many inverters, or whatever components you want that you have trained for, with the pin, and use it in a commercial, conventional, whatever you want to call it, simulator. Okay. Because what happens in the simulation is that all the components are described by differential equations, and then we have the algebraic ones that have to reconcile voltages and currents. This is the power flow equations. The y equals yv, I guess you get that this is the admittance matrix, right? This is what they need to be reconciled. Good. So it's a plug and play. Now, we did some tests in 3 different systems, 9 bus, 14 bus, 30 bus. We replaced one generator, inverter-based generator for us, with a pin in each case. Okay. And I have some results for all 3 systems. So for the same time step, the accuracy increased up to 50% of estimating. Here I just only have two variables, omega or current, but I will also have other variables, and we see the improvement there too. And on average, let's say for all the frequencies that had a different, because every component has its own frequency, we increase the accuracy of the system. Okay. Increasing accuracy means that I have the opportunity to perform longer time steps. That's the whole idea. Because the only thing that limits my time steps, so how fast I can move forward and solve it, is how accurate I am. If I have too large errors, I need to take very small time steps. And now this is, let's say, a trajectory, just to see how this looks like. This is a traditional or conventional solver, and this is, for this 30-bus system, 1 pin, 6 conventional ones. You can see that the error accumulated is actually smaller. Okay. Yes, Alex. By what? Sampling. Something like Nyquist. So you have to be smart how you sample during the physics from training, these collocation points that we call it, because these are just generated. So you just sample a point and you validate the equations, or you evaluate the equations to make sure that they comply with the physics, right? I'm not sure about the Nyquist, if you're bound by that, but you need to perform a good enough training. Yeah. And that's also an art. I haven't checked if that actually satisfies the Nyquist theorem or not. Okay. So we have created actually a toolbox that's also open source and free for you to use if you want to train a physics-informed neural network for any component that you want. Okay. And contains the definition of the ODEs, generates the data set, it does pre-processing, it has the training of the pin, and then you also evaluate and visualize. Yes? It actually works very well. Then depends. So the question is, what if I increase the number of the pins, what happens to the error? Depends what kind of pins, so what kind of components you replace and how well you have trained the pins. But in general, if you have, let's say, similar pins and similar components that you replace, then the error remains like that, right? Yes, you can. So you can have a system with all pins, no synchronous machines. Yes, you can have that, yes. And can replicate the behavior of the synchronous machines without any problem? Yes, yes, it can. Yeah. Question, yes.
Time simulation. For example, if you want to simulate some transient that involve to give some output within a microsecond.
The question is how fast can a pin simulate a transient simulation if it can go to microseconds? I mean, the easy answer would be yes, but the question is what exactly is the system that you want to simulate and what exactly is the pin, right? We can talk about trajectories. We are in the milliseconds at the moment. But if you optimize what you want to do, then you can also go down to microseconds. Okay. So if you want to estimate just a single point and the pin is small enough, then you can have I don't know. Microseconds is actually very, very fast. Maybe you need an FPGA to estimate to have a pin. You have a neural network on an FPGA, maybe, I don't know. Very good. And now with this toolbox, we also did some tests comparing the ODE solver with the pin. You can see that there's benefit when we do a lot of trajectories, right? As I was saying, for a single trajectory, we need about 2 milliseconds with a neural network or the pin, when it takes about 10 with ODE. But the true benefit comes if I want to do 500 trajectories. Because then it's really about 63 times faster, because of the GPU parallelization, as long as I have a well-trained neural network, I can just generate a lot of trajectories. Okay. Questions? Good. I have a couple more slides and we finish. Okay. Are pins scalable? So we discussed about, let's say, yeah, can we have a single bus for a single pin for 1,000 buses? What do you think? I say not, and actually, we have tried, to be honest. So the first idea we had, because we were the ones that actually introduced pins in power systems, was to have a pin for, let's say, 1,000 buses, 118 bus system or whatever, right? We never managed to make it work. Okay, it's very, very complex. There are so many variables. I don't know, you need a hypercomputer or you need a neural network with, I don't know, a deep neural network to be able to capture everything. So it didn't work in terms of training. And also, it's also very, very inflexible. So if something changes, so let's say if the topology changes and I have only trained for one topology, I need to retrain, which is actually a major barrier, right? So for us, after spending 2.5 years on that and failed, this was not the way to go. But then we figured out a different way. Okay. So it took 2.5 years to figure this out. And that's actually the learnings that you get from failing a lot, right? And we don't discuss that so much. And we came up with this concept called pin sim. So what is pin sim? I have a single pin for every component. And this is a vision that we have, and we're starting to build that. That's part of the toolbox that I also showed. I want to create a library of pins. Similar when you do simulations, you have a library of models, right? You have a library of models and you do plug and play. You take that model in, you connect them, and then you press play, and then it simulates. So these models actually do not change much. You might set some parameters, but you can also have inputs for the pins for different parameters. So I have now a library of pins. I want to drag and drop them. Let's see how, because this is just a GUI. The first task is to create the simulation engine behind. Connect them together and solve them all together. Okay. And we already are trying a few things, and we see that there is a significant time benefit. I mean, 10 times faster plus. Our goal is 100 times. And there's also a lot more opportunities, because with a conventional solver, we are bound by how the legacy systems are, which means that if I also want to have conventional models in, I can only move one step ahead. What we are looking at is with pins, I can maybe compute for the next 10 steps at the same time, right? And then I can be much faster in generating the trajectories. So there are a lot of different ideas. We're working on that. But then the idea would be to have a simulator completely based on neural networks. Yes? How what? How bound are these models to parameters? And actually, that's a design criterion. So if there is a parameter that you change often, then you enter it as a parameter, as an input to your neural network. You design it like that, and then you can change it as you wish, and you don't need to retrain. You have already trained for a range of these parameters. What you are bound from is the range that you train for as an input. Okay, but it's the same. Sorry, it's the same with the conventional models. I mean, these models are accurate for a range of conditions, right? And it's the same with neural networks. And I just want to say also one more thing. We take these tools like PSCAT for granted, that they are the holy grail or whatever, they are always accurate. It's also a numerical solver. Sometimes they fail, and we don't realize if this is a numerical error or if this is really a blackout, right? So, but people trust them with, like, blindly, without actually thinking that they also have trust issues there as well. Yeah. So pins versus neural networks. So the question is, if we put in the required amount of time, and maybe data, I guess you mean, right? If neural networks will work the same as pins. And if they are going to work better than pins? Okay, if pins do something differently. So, no. If we have the required amount of data and the required amount of time, then neural networks will work exactly like pins. Okay. The only reason we use pins is because, especially for systems with differential equations, it's faster. We have seen it's faster to have pins compared to the standard ones. Yeah. Yeah.
So from what I understand from your previous slide, you only tried feed-forward neural networks, or have you tried different kinds of models?
We only tried feed-forward neural networks, yes. But what different kinds are you thinking of? No, we have tried a few more things, sorry, yeah. But what are you thinking of?
Maybe a LSTM or...
So maybe LSTM, yeah. LSTM, no, because it's for time series. And it's time series prediction, so it takes... Understand that this is a trajectory, so you might want to say that, I mean, I take into account, I have memory of what happened previously, so I predict what happens next. But no, we haven't tried LSTMs.
Because you mentioned as time goes on, the accuracy drops. So I'm wondering if maybe if you tried a different model, it could counteract that. Maybe some other models work better.
We have tried different forms of neural networks, and I'm also going to discuss briefly about CANs, which call Mogorov-Alnord networks. And now we're working with ACNets and different, let's say, neural operators, but not LSTMs. And somehow, I don't think we're going towards LSTMs. Because we think that this is more, LSTM is a recurrent neural network, well to predict time series. You need to put the physics in there. Yeah, I'm not sure if this is going to, yeah. Is it possible to do hybrid simulations in PinSim? What do you mean by hybrid? To have traditional components. The way that we are designing right now is only pins, because we want to actually get the speed up that pins can allow us to get. And if we have traditional components, then we need to stick to the legacy simulation system, right? For that, we have the integration of pins to the existing simulators. Right? Thanks. But nothing excludes that in the future, right? I mean, you can build something that works like that. Other questions? Okay. Then, my other question is if pins are trustworthy, and we also discussed that there's no guarantees, no performance guarantees about pins. They are as trustworthy as any reduced order model. Okay. Or to be honest, as any model, if you want, that we use. So the difference is, of course, that reduced order models come from first principles, or the models that we have, the conventional ones, have been somehow validated, or they comply with some physics that we can better understand. When you see a neural network, you don't understand how the input connects to the output. That's an issue. What we're working on is on verification of pins, which is not an easy task, because we need to consider the differential equations. And that's not easy. We're going to talk about verification right after the break. We have done some work here, if you want to take a look at. And there's also some work about this error certification. Yeah, about pin verification. It's an open topic. If somebody finds a way to do that, the cool thing with that is that for the first time we'll have let's say a worst case guarantee for any reduced order model. Right now, reduced order models in power system, they just say they work well for this area. I mean, it's only by inspection or by there are no formal guarantees, right? If we do that with pins, we'll be the first that we can have some guarantees about model equivalence. Yeah, and if you're interested in PhD or postdoc and these kind of things, then please let me know. I'll stop here. We have a break. There's a Google Colab that you are welcome to play with. Actually, it's Indrajit with Rahul and Ignacy that did that. This is here. It's also on the slides. If you want to play during the break, you're welcome to play with it during the break. It actually has the standard swing equation that we showed, with training a pin. All the code is there. You can train a pin yourself and see how it works. I will leave it actually here. And then, if you want, you can also answer these kind of questions to see how one does that. Any questions so far? Let me just discuss maybe one thing that also came up during the break, because there was a question, how do we handle faults, right? And when we're discussing about this, the pin sim, so for this part, or for the one that we integrate a pin to a conventional simulator, we don't really need to handle faults during the pin training. We train a pin for a component. The fault will actually happen not inside the component, but somewhere out here, right? So if I have a three-phase fault here, I just need to set the voltage here to 0, and then the pin should react to that as any conventional model. It's the same process that will happen with any conventional simulator, okay? So this is the idea. And then, for example, if there's a relay or so you trip and then you actually reclose, then actually you need to just bring the voltage back up and then see what happens. But we are not bound by that. I mean, pin sim, and if you integrate to a normal simulator, then this is handled. There's no barrier there. And no need to train for that. As long as you have trained for a 0 voltage in your pin, right? You need to have captured this range. Good. Let's move now to trustworthy AI for power systems. So I will start a little bit more general. I mean, AI, if you really think about that, has already offered value in energy systems, right? And we discussed already about this. Forecasting is one really cool or really good application where AI has found or has generated a lot of value for power systems. That's load forecasting, weather forecasting. We also talked about predictive maintenance and energy trading, right? I mean, we already discussed about that, so I guess that you are somewhat familiar. I'm just going to mention that about load forecasting, the first machine learning or neural network, let's say, that was used for load forecasting was the 90s, developed by EPRI in the US, and used actually in 32 utilities by 1997. So they trained a neural network to forecast the load. Weather forecasting, we also discussed that with Francois the previous days. Right now, this kind of AI models are better than physics-based models. Okay. They can predict the weather with higher accuracy. We discussed about predictive maintenance. Let me go directly here. What do you think we see here? Because I find this picture very interesting. A satellite image of oil tank levels. Very good, you actually got close. It's a satellite image of, I think it's a oil tank or hydros, or water tanks. But indeed, actually, it's a satellite image of tanks. You can see how much actually, I think it's water level. You can see what is the water level on each tank, so how much actually they have to produce. They have enough to produce. And by that, they can predict prices, which is actually amazing. And because I also have a friend working in this field, not in energy trading, in trading in general, it's crazy what kind of ideas they have on how they can, where they can get public info to predict prices, which I find very interesting. It's a lot of innovation. Very good. So, but then also we have Gen AI, and we're also discussing now what Gen AI can do for us. Right now, the actual use cases being discussed, to be honest, there are maybe, from a research or from my research perspective, a bit less, let's say, interesting, but it's, you get the whole manual or the whole procedure of how, let's say, you replace a transformer if you want, or a small component through ChatGPT or the equivalent. And then when technicians go out in the field and they need to replace something, instead of having to read the manual, they have an AI assistant telling them step by step what are the things they need to do. which I think is amazing, right? And that's one of the immediate use cases that Gen AI is going to use, crunching up large documents. At the same time, I mean, I found this interesting, I don't know, discussion on Twitter. Actually, my wife sent that to me. So I wonder how much money OpenAI has lost in electricity costs from people saying please and thank you to their models. And then Sam Altman, the CEO of OpenAI, says probably millions, but you never know, right? So, and by that, actually, this gives me a very nice, I don't know, for me at least, step into would we ever trust this kind of large models, or in general, AI, to run our electricity network, right? So my question to you is, what would you do to make it trustworthy? Because right now, if you go to any control center or let's say any operator, they won't allow you or they won't let you actually put AI into their control room. Although, from what we have discussed, maybe the senior management would like to see AI methods there, right? So what would you do? Yeah.
Performance guarantees or feasibility guarantees.
True, performance guarantees or feasibility guarantees, very good. Yeah, what else? How would you use AI to make sure that it's somehow trustworthy? Yeah. Present decisions in a way that operators can understand. Very good. Okay, but then who takes a decision? Who takes a decision? So the operator takes a decision, but you present decisions that operators can understand as a decision support. So what you're saying is you need to understand, so you need to let the operator understand why you propose that decision as an AI, because otherwise the operator will not be convinced to take the decision. And metrics that are convincing for us might not be convincing for the operator. Okay, I'm just repeating so that it's also people can hear it. Very good, yes? So somebody wanted to say? To provide decision support, you said? Yes, yes, very good. Anything else? Yes, sir. Yes? To have a study that an operator with a tool makes better decision than without the tool. The operator still makes the decision though, right? Yeah. Okay, very good. Yeah. Lobby to the lawmakers to enforce the implementation of the AI. Very good. What happens if the AI makes a mistake and we have a blackout? On top of, okay, on top then also to somehow, yeah, I mean, policy is important. It's actually a huge enabler or a barrier, right? Yeah, policy is important for that. Yes? Open loop operation for a while, which means? So then, yeah, the AI takes decisions, but actually are not implemented just to show to the operator that it can take good decisions and start building the trust. Yeah, very good. It's a good point. Actually, this is also used in trading. So there can be a test phase of 2 months showing that the AI tool you developed takes better decisions than maybe another tool you had, and then you can start trust that. Yeah. Very good. Train the operator with the AI from early in their career or in start, so that they get familiar and start trusting that. Very good. Yeah. Yeah. Very good. So put some performance guarantees at least on the worst outcome. So you have guarantees about the worst case violation, the worst outcome. So even if you don't have the optimal, you have a near optimal solution, right? Yeah, with no violations. Very good. Very good. Very nice. I can just tell you what I have collected, which is actually only a small set of what you said. So the first is performance guarantees. Okay. Performance guarantees in the sense that I can verify the output of the neural network that does not violate constraints, or I can determine what's the worst case violation. Okay. Then I can tell the operator that, you know what, if you get this, then the worst case that can happen over the whole operating region that you will operate your tool, it will be, I don't know, this % of violation, right? And that's what we're working on. Now, with this, you actually get a stamp, if you want, of a verification stamp or whatever you want to call it, or validated that then you can deploy it. Then it's safe to get that and deploy it in the, as it is. So it can work well, I think, for controllers. Any kind of control actions you want to do, then maybe you want this verification. The other, at least the family I have tried somehow categorize that, is as decision support. And that's actually a lot about what also Pascal discussed. I take the AI output, and then I project it in the feasible space. If I project in the feasible space, then I'm guaranteed to be feasible. I can trust the decision. I can trust what the output is, right? I can take the AI output and I use it as a warm start for a nonlinear optimizer. I can take and I can use my AI to actually predict or estimate what are the active constraints. This can help me solve difficult optimization problems. So we have done that as well. You can take difficult MILPs or MINLPs by predicting the active set. Intractable problems become tractable. Okay. And for warm start maybe as well. Or you can use the AI to screen millions of scenarios. That's what we were discussing about physics-informed neural networks. We screen a lot of scenarios. There is no criticality in there. And then we take the critical ones and we actually simulate them more in detail. Okay. Very good. And that's what I'm going to discuss, at least in the rest of this talk is going to be about how we do this verification. Okay? And there's a rigorous way to do that. So I'm just going to talk a little bit about developments, at least in Europe, but I know it's also coming in the US. I know there was a White House kind of conference about trustworthy AI last year in the US. To be honest, I'm not sure about Canada. In Europe, people are much more skeptical towards AI, which means also that we need more trustworthiness. So Margrethe Vestager, who happens to be Danish, by the way, and was visiting us as a commissioner at that point, passed a kind of regulation, if you want, or directive that's now is in effect since last August 2024, about a Europe fit for digital age, saying a lot about trustworthiness, right? Trustworthiness not only in the sense that we discuss it here, but also how you get data, what happens with the data, how the AI can process data of consumers and things like that. So there's a lot of things, and there is also a separate clause about safety critical systems where we fall into, and what should happen with them, how they should be regulated. Now, Gurobi, as well, where Andreas' affiliation, or one of the two affiliations is, also has now modules that can deal with neural networks, because as we will discuss today, the verification of a neural network in the most standard form is an MILP. I solve a mixed interlinear program, and that's how I verify. And Gurobi is really good at optimization, especially MILPs. So they actually create a module to do that. It's not only that, there's also actually a competition taking place. It's now in the 6th edition this year, verifying neural networks. And there is this cool team, actually, that developed this so-called Alpha Beta Crown that is a dedicated solver. It's an optimization, to be honest, that they are solving to verify neural networks. And why is this important? Let's forget a bit our field, right? What do we use AI for? We use that a lot for image recognition. And the market there is much larger, right? Think about all the safety critical systems or situations or applications that have to do, I already have it in my screen. Yeah, okay. That have to do with image recognition. Two of them are MRIs, so medical resonance imaging, right? If I want to detect a tumor or detect something that's abnormal, soon, or maybe even already now, I don't know, it will go through an AI and will help the doctor decide if they see something or not, right? But this AI tool should be trustworthy. If it misclassifies 50% of the time, or if it cannot actually do its job correctly, then we cannot really trust it. Then this kind of tools like Alpha Beta Crown come in and try to verify that there's no misclassification, okay? At least in certain regions. Same for self-driving cars. I need to make sure that when I see a red light, it's a red light and I don't think it's a green light, right? It's very important for my AI tool, because it's going to be an AI that's going to detect a green or red light, that it does not make a mistake, and I can verify for that, okay? So this is some of the use cases that have been used. Now, since last year, we also have use case about AC OPF, and now also there is in the newest, let's say, paper that they published, or let's say put online, that have the newest version of Alpha Beta Crown, they also talk about the use case about AC optimal power flow, so we're getting noticed, which is very nice. Okay. Now, what we did in some of our work back, I think, yeah, almost 1.5 or 2 years ago, we reformulated Alpha Beta Crown to use it for OPF, which is not straightforward, because Alpha Beta Crown just says if it's violates or not a constraint, a single constraint. But what we want to do is we wanted to make sure that it does not violate any line flow constraints. So imagine a system, I don't know, what we have here, 300 bus. So this is like 500 lines. I want to make sure that does not violate any of the 500 line flows. What Alpha Beta Crown is built to do is to make sure for a single constraint every time. Okay. So we made some reformulations which were quite efficient, and then we compared that with Gurobi. And Alpha Beta Crown is actually 7 to 300 times faster than Gurobi. Okay. So what you see here is actually for different, let's say, generation levels to cover the specific load. Then you see that this is not safe, not safe, not safe, and then 1.2, this is safe. Okay. So you can see that as long as it's not safe, it's very easy to verify that I violate a constraint. Because the first constraint I violate, I'm done, right? The difficulty is to verify that it is safe. Because I have to be safe for all constraints, and we're talking about thousands of constraints. And that's why Gurobi here takes forever, and then Alpha Beta Crown manages to do that. Obviously, 3 times slower, but still quite fast. Okay. So it is a quite difficult problem to do. Now, besides verification, there's also interpretability, and we discussed a bit about that. So to give, let's say, decisions that can be somehow, they have some meaning. There is a sub toolbox out there. I also have the link there. It's free for you to use. I think it's really cool. It's almost off the shelf. You can take it and apply it on any model that you have, let's say decision tree or neural network. What it tells you is sensitivity of the output with respect to the input. So this means that if I am, let's say, here what we did is, if my PV's output is more than the load, then I can actually understand which is the feature that has the most impact. If it's, let's say, the temperature or the irradiation, things like that, right? But you can actually test that. In terms of interpretability, I just have 2 slides because we talked a lot about physics-informed neural networks before. These are the standard, if you want, multi-layer perceptrons. There are new ideas. One of them is this Kolmogorov-Arnold networks. What's the cool thing about them? So here we have the standard activation function, that's ReLU. So we decide just how many neurons we have, how many layers we have, and then we train the weights and biases here, right? What the cans do is, the cans have this activation functions as part of their training. So I can have much smaller networks because I don't need so many activation functions. I can have any activation function, okay, usually polynomial here, but I train for this. So I can have a much smaller network with activation functions that can probably tell me something about the inputs. Okay, so they are more interpretable because they are smaller and because the activation functions give me some more information. Then we made a test in terms of accuracy and in terms of speed. They can be, or they are, or they can be, I guess, more accurate than the standard pin, which is very nice, at least in some cases. But they're also a bit slower than the standard pin because there's more operations happening inside the CAN. Just to give you an idea where we are going. Now, besides CANs, there are also different kinds of neural networks. You don't need to limit yourself just in one architecture, right? A lot of things are coming up in the machine learning domain, sometimes difficult to keep up. Very good. So theoretically, I have 10 more minutes. Let's see what we're going to do. So I want to talk a bit about verification, okay? I think we can do that in the next 10 minutes. What I'm going to talk about is that essentially AI needs OR. So the ones that actually do OR or AI, they're well placed to handle a lot of different problems. The major challenge, and I think Pascal said that as well, is tractability. So how do we scale up to larger systems? And that's an open question. We're always trying to become better. New methods appear. Of course, it takes some time. Let me jump into how we do the verification to give you the intuition and how this works, right? I'm going to talk about two types of verification. First, I'm going to focus on classification neural networks, okay? In order to make that more concrete, it's good to have an example. So let's work with an example. The example is, I want to assess if an operating point is safe or unsafe. So I have a database of operating points. You have seen that also earlier today. I train over all these points, safe or unsafe. I want my neural network to tell me if a point is safe or unsafe. Okay. So what happens? As long as I have a neural network with ReLU activation functions, and I'm going to say what this is, but this is the most common activation function, I have an exact transformation. I can transform a trained neural network to a set of linear equations with binaries. Okay. As long as I have converted that to a set of linear equations with binaries, I have converted all the information that the neural network has into this set of constraints that can then include into an optimization program, okay, into an MLP. So I do that, and then I assess if the neural network complies with the ground truth. So here is how this works. Neural network, 2 layers, 2 neurons per layer. The activation function is the ReLU. What this is, a piecewise linear function. When the input is positive, the output is equal to the input. So that's the y equals x. When the input is negative, the output is 0, right? So this 0. So I can reformulate that with binaries. So if the input is negative, then the binary is 0. So because keep that to 0. If the input is positive, then the binary is 1, right? And I can encode all these operations in a set of linear equations with continuous variables and binaries, and integrate that in optimization, as we said. Let's see how this works. This is now a real case. I think, again, it's from the 14-bus system, but we have also done with 118. So, again, 2D projection. We have generated all these dots that you see there, right? Because we wanted to test how our verification method works. Normally, you don't need these dots. We did that in order to see how this works. Okay. So what happens here is, I take one point here, my reference point x, where I assess, or so I know the ground truth. I know that this point is safe. What I can verify for is, tell me the maximum distance, or here, what I want to say, let's see. So for a specific distance, epsilon, from this reference point, tell me, does the classification change or not? If the classification does not change, that's an optimization problem, right? If it stays, let's say, the same, then I can verify that all this region will be classified as safe. Why is this important? Because I don't need to test for any points within this region anymore. I know that all this region from the neural network point of view, it will be classified as safe. And if I have, let's say, a nonlinear boundary, then I can generate a lot of different this kind of regions, and I can verify for these patches. And this is continuous regions. I am not discrete anymore. I'm verifying for continuous regions. And if I know that this region now in the ground truth is safe, then I'm good. I know that the neural network is going to actually comply with reality. That's an exact, there's no approximation here happening. That's an exact transformation. Okay, continuous regions. For the first time, we're able to do continuous compared to the past that can only do testing of samples. Questions? Because I'm going to build up on this. So it's good if, yeah. How do I verify if it's correct, or how do I verify if it's in the same class? Yeah. Yeah, then for this case, you have actually to check with the ground truth. So this is the next step. But now I'm going to build up on that, because now we're going into power systems. So this is for any image, right? In an image, I don't have the ground truth. I need to validate somewhere else. But for us that we have the equations, we can do something better. Any other questions? Okay, let's see how we actually improve on this. And we go now to provable worst case guarantees that we actually came up with. So what happens? The main idea here is that we take advantage of the ground truth. I can formulate the ground truth in terms of equations. And if I can formulate the ground truth in terms, let's say, for an OPF, I have my power flow constraints. I can put these constraints inside my verification problem. And now I no longer need to say if it changes class, but rather say, how far do I evaluate this constraint? Because this constraint is now part of my optimization problem. Let's see how this works. The cool thing for this is, again, no discrete sampling. I verify, or I find the worst case evaluation for a continuous domain. I don't do sampling. Yeah, and we use, yeah. So let me, I don't have the formulation here. Yeah, I decided to skip the equations to not make it a bit lighter. But the idea is actually that the idea is that I minimize the worst case violation subject to the neural network and the constraints, right? So get me what is the, I maximize the worst case violation. Let's see some results, and then we can discuss. If you have questions, I will pull up the slide of how we do that. So we tested for 7 different test systems. The worst case violation over the training data set, the whole training data set, of generator limits, so if it exceeds the maximum limit of the generator, and line limits. Okay, if it exceeds the maximum line limit. So we only use the training data set that we have used, but all these points. And then we have the exact worst case guarantees. That's actually the domain within where these points live. We validate or we verified for the whole continuous domain of that. Okay. What do you expect to see? Okay, do you expect higher violations in the exact worst case guarantee compared to the empirical one or the data set, or lower? Yeah. Higher violations, right? I mean, this is, at the end of the day, this is a discrete subset of this whole input region. If either this gets exactly the same value as this one, or this will be higher, right? How much higher? So if I say, if I have covered actually quite well my space, right? Which means I get 98, 99% accuracy on my discrete set, or average error, let's say, of 0.4%, whatever. So 0.4% MSE. What kind of worst case violations do you expect to see? How much higher do you expect them to be? Just, I mean, intuitively. What do you think? I have an average error of, let's say, 0.4% over this whole training data set. What kind of worst-case evaluations do you expect to see? Was that? 10% worse. Okay, so 1.1 times worse, right? Yeah, 10% worse. Yeah. Okay, let's see. For the 300 case, this is the evaluation that we found over the set. So this is the worst case evaluation on the discrete set. And the worst case is actually 7 times higher. So there's somewhere a point in this continuous input domain that we have not picked as a sample that leads to 7 times higher evaluations than what we're able to identify through our training data set. Okay. And that's why it's important to get these worst case evaluations in, as long as you don't project. When you project, then of course, into the feasible space, then you remove this kind of violations, right? The other cool thing is, though, that you can also verify and get a 0 violation. And if you get a 0 violation, this means that for this 57 bus system, for the continuous input domain that you have trained, there is no violation of the lines or the line limits. Which means you can go to the operator and tell them, use this AI to do your OPF. It will never violate the line flow constraints. Okay. And to be honest, that will be the ideal for us. To develop tools that actually arrive at the 0 is not easy. But that's the goal. Okay. Good. Questions so far? Now, one of the questions that we also, we actually have asked ourselves a lot of different questions, but one of the questions we also asked ourselves is, how do we reduce these violations? Okay. What I show here is DCOPF. We've also done that for ACOPF, but what I show here is DCOPF. For these exact same systems, what we have seen is that the violations, or the worst case violations, are on the boundaries. So what would be, let's say, I think a smart trick to do? Train on an input region or train on some region, but then apply the neural network only on a subset of that. So train for this, let's say if that's a box, train on all these, but only use the neural network on this smaller subset. And that's how you can actually reduce a lot the violations. Okay. Now, we thought that this actually happens because this DCOPF, it's a linear program. Probably the violations would be on the boundary. But we have also seen the same behavior for nonlinear problems. Okay. So it appears that the boundary, that if we train on a larger domain and then apply it on a smaller one, it has quite some good potential to work without violating a lot. Okay. This actually brings me, so here I have a few options for you to decide, but it's already 4:15, so I guess this leaves us no other option, but rather than conclude and discuss, okay? So in the slides that you have online, I also have material about graph neural networks, and I also have material about how we can integrate worst-case violations in the neural network training, which is actually to some percent aligned with what Pascal discussed also this morning. Okay. So the idea for us, and let me just briefly discuss this, is, okay, now what we discussed here is I have a trained neural network, and then I determine the worst-case violations. What we have worked on and continue working on is I want to minimize the worst-case violations during training. So by the end of the training of a neural network, I also get a guarantee that this is, you can violate 10%, and that's it, right? But I have minimized this worst-case error that I get, which also has differentiable layers that Pascal also mentioned this morning, and a lot of other tricks to do that. Okay, so I'm just going directly to the conclusion. Okay, any questions? Very good. So, I mean, if you really go into the domain of neural network verification and trustworthiness, I mean, if you look at the machine learning community, there's like already a lot of methods being discussed. What we're trying to do is we tried to, in this paper, to classify a bit the different verification methods, and we're working on this kind of trustworthiness toolbox that will hopefully be up in the next couple of months, so that then people can use it also for power systems, right? What is the vision? We're now part of a European project called AI Effect, and there's also, I think, 2 sister projects on that. The EU is pushing for validation or explainable AI in power systems. Okay. So what does this mean? They give funding to develop test and experimentation facilities that can validate, verify AI tools for power systems. So the idea is that there is any vendor coming, any vendor that designs an AI tool, they come to us or to some kind of certification facility, they test it, they validate, and they take a stamp that is now certified, it works in this domain, or it works with this kind of error, right? And then they can go to an operator or to any of their clients and tell them, you know what, now this is certified, you can use it. That's the idea. So the idea for us is to develop a sandbox, to try and test things, consult them how they can improve the performance, and give them the certificate of performance. Okay, this kind of performance certificates, which I found very cool. And I think or my vision, at least for that, is we need to develop or to evolve towards AI standards for the tools. We are still early, so we don't know what kind of standards we need. But if we develop the standards and then vendors comply with the standards, then also operators will be open to use them, right? So that's the idea. Maybe in the next 5 years. Final thoughts. We talked about speed up. Pascal talked about speed up. It is actually a lot of things that happen in power systems that they need faster solution algorithms. If we want to accelerate 10, 100, or 1,000 times, conventional tools, I think, won't get it. So we need to think differently. AI could be an option. Okay. At least for us, it's definitely a way to go. You can think of different things. But if you want to be disruptive, think about how you can achieve that. AI needs OR. So you saw that neural network verification is an optimization problem. It's actually an MILP. And if we go to nonlinear problems, it's MINLP. Okay. So we need people that are good in operations research, in optimization, and at the same time in machine learning, and if you want, also dynamics, right? Can we model the ground truth? If yes, then use it. Okay. Physics for neural networks is one of them. Then sampling beyond the statistics that I showed at the beginning is also using the underlying network, or let's say the underlying knowledge, and the worst case guarantees. And we also talked about PinSim, which is a simulator that is based on physics from neural networks that can possibly accelerate things quite a lot. It's a new concept. What are the challenges? Scalability is the main one. Topology is another one. Graph neural networks might be able to overcome this. PinSim actually is overcoming that by being very modular. So we train for every component, and then we bring the components together. We should develop methods that are not hard, where the topology is not hard-coded, if you want, right? And then Gen AI is coming. And how can we take advantage of that? I mean, this is still an unexplored territory, right? The developments are so fast, and we need to see how we can take advantage of them. I just have here collected the toolboxes that I shared, and then I will stop here. Thank you very much.